And back with structure and interpretation of computer programs. So we arrived at chapter 3, modularity, objects, and state. So even while it changes, it stands still, which I guess that in Italian is e pur si muove. I don't know. And this quote is from Alphonse Carr. Plus a change, plus c'est la même chose. Plus a change. Okay. So the preceding chapters introduce the basic elements from which programs are made. We saw how primitive procedures and primitive data are combined to construct compound entities, and we learned that abstraction is vital in helping us to cope with the complexity of large systems. But these tools are not sufficient for designing programs. Effective program synthesis also requires organizational principles that can guide us in formulating the overall design of a program. In particular, we need strategies to help us structure large systems so that they will be modular. That is, so that they can be divided naturally into coherent parts that can be separately developed and maintained. Yes. One powerful design strategy, which is particularly appropriate to the construction of programs for modeling physical systems, is to base the structure of our programs on the structure of the system being modeled. For each object in the system, we construct the corresponding computational object. For each system action, we define a symbolic operation in our computational model. Our hope in using this strategy is that extending the model to accommodate new objects or new actions will require no strategic changes to the program, only the addition of the new symbolic analogs of those objects or actions. If we have been successful in our system organization, then to add a new feature or debug an old one, we will have to work on only a localized part of the system. To a large extent, then, the way we organize a large program is dictated by our perception of the system to be modeled. Let me check if I'm recording. Yes. Okay. In this chapter, we will investigate two prominent organizational strategies, prominent organizational strategies arising from two rather different worldviews of the structure of systems. The first organizational strategy concentrates on objects, viewing a large system as a collection of distinct objects whose behaviors may change over time. And an alternative organizational strategy concentrates on the streams of information that flow in the system, much as an electrical engineer views a signal processing system. Okay, of course, I already heard about object-oriented programming and object-based approach, while the stream processing approach is totally new to me. So let's see what this approach is about. Both the object-based approach and the stream processing approach raise significant linguistic issues in programming. With objects, we must be concerned with how a computational object can change and yet maintain its identity. This will force us to abandon our old substitution model of computation in favor of a more mechanistic but less theoretically structurable environment model of computation. The difficulty of dealing with objects, change, and identity are a fundamental consequence of the need to grapple with time in our computational models. These difficulties become even greater when we allow the possibility of concurrent execution of programs. The stream approach can be most fully exploited when we decouple simulated time in our model from the order of the events that take place in the computer during evaluation. We will accomplish this using a technique known as delayed evaluation. Is delayed evaluation the same of lazy evaluation? We will see. So section 3.1, assignment and local state. We ordinarily view the world as populated by independent objects, each of which has a state that changes over time. An object is said to have state if its behavior is influenced by its history. A bank account, for example, has state in that the answer to the question, can I withdraw $100, depends upon the history of deposit and withdrawal transactions. We can characterize an object's state by one or more state variables, which among them maintain enough information about history to determine the object's current behavior. In a simple banking system, we could characterize the state of an account by a current balance rather than by remembering the entire history of account transactions. Yeah. In a system composed of many objects, the objects are rarely completely independent. Each may influence the states of others through interactions, which serve to couple the state variables of one object to those of other objects. Indeed, the view that a system is composed of separate objects is most useful when the state variables of the system can be grouped into closely coupled subsystems that are only loosely coupled to the other subsystems. This view of a system can be a powerful framework for organizing computational models of the system. For such a model to be modular, it should be decomposed into computational objects that model the actual objects in the system. Each computational object must have its own local state variables describing the actual object state, since the states of the system since the states of the objects in the system being modeled change over time, the state variables of the corresponding computational objects must also change. If we choose to model the flow of time in the system by the elapsed time in the computer, then we must have a way to construct computational objects whose behaviors change as our programs run. In particular, if we wish to model state variables by ordinary symbolic names in the programming language, then the language must provide an assignment operator to enable us to change the value associated with the name. Yes. Local state variables. To illustrate what we mean by having a computational object with time-varying state, let us model the situation of withdrawing money from a bank account. We will do this using a procedure withdraw, which takes an argument as argument an amount to be withdrawn. If there is enough money in the account to accommodate the withdrawal, then withdraw should return the balance remaining after the withdrawal. Otherwise, withdraw should return the message insufficient funds. For example, if we begin with $100 in the account, we should obtain the following sequence of responses using withdraw. So you withdraw 25 and the procedure returns 75. Again, withdraw 25, the procedure returns 50, but if you try to withdraw 60, the procedure returns insufficient funds. Whereas if you try to withdraw 15, you get 35. Okay? Observe that the expression withdraw 25 evaluated twice yields different values. This is a new kind of behavior for a procedure. Until now, all our procedures could be viewed as specifications for computing mathematical functions. A call to a procedure computed the value of the function applied to the given arguments, and two calls to the same procedure with the same arguments always produce the same result. To implement withdraw, we can use a variable balance to indicate the balance of money in the account and define withdraw as a procedure that accesses balance. The withdraw procedure checks to see if balance is at least as large as the requested amount. If so, withdraw decrements balance by amount and returns the new value of balance. Otherwise, withdraw returns the insufficient funds message. Here are the definitions of balance and withdraw. To define balance, 100 is the initial initial balance. Okay, define withdraw amount, so the procedure, and check if balance, begin, set. So if balance is greater than the amount that you want to withdraw, basically this, and then there is this begin set. Decrementing balance is accomplished by the expression set balance set balance. This is the assignment operator, I guess, or the assignment, yeah. Set special form of syntax is set name and a new value. Okay, begin. What is begin? A list of instructions. So first you set and then you return a balance. Yeah. So here name is a symbol and new value is an expression. Set changes name so that its value is the result obtained by evaluating new value. In the case at hand, we are changing balance so that its new value will be the result of subtracting amount from the previous value of balance. Withdraw also uses the begin special form to cause two expressions to be evaluated in the case where the if test is true. First, decrementing balance and then returning the value of balance. In general, evaluating the expression causes the expressions x1 through k to be evaluated in sequence and the value of the final expression xk to be returned as the value of the entire begin form. Okay, so here we have just two instructions in the begin block. So first we set the new amount, the new balance, and then we return the balance. Otherwise, but this goes with the if, we return insufficient funds. Okay. Although withdraw works as desired, the variable balance presents a problem. As specified above, balance is a name defined in the global environment and is freely accessible to be examined or modified by any procedure. It would be much better if we could somehow make balance internal to withdraw, so that withdraw would be the only procedure that could access balance directly and any other procedure could access balance only indirectly through calls to withdraw. These would more accurately model the notion that balance is a local state variable used by withdraw to keep track of the state of the account. And we can make balance internal to withdraw by rewriting the definition as follows. Yeah, basically we define, instead of using define balance 100, we use the let. And then we use lambda to define our procedure. What we have done here is to use let to establish an environment with a local variable balance, bound to the initial value 100. Within this local environment, we use lambda to create a procedure that takes amount as an argument and behaves like our previous withdraw procedure. This procedure, returned as the result of evaluating the let expression, is new withdraw, which behaves in precisely the same way as withdraw, but whose variable balance is not accessible by any other procedure. Combining set with local variables is the general programming technique we will use for constructing computational objects with local state. Unfortunately, using this technique raises a serious problem. When we first introduced procedures, we also introduced the substitution model of evaluation to provide an interpretation of what procedure application means. We said that applying a procedure should be interpreted as evaluating the body of the procedure with the formal parameters replaced by their values. The trouble is that as soon as we introduce assignment into our language, substitution is no longer an adequate model of procedure application. As a consequence, we technically have at this point no way to understand why the new withdraw procedure behaves as claimed above. In order to really understand a procedure such as new withdraw, we will need to develop a new model of procedure application. In section 3.2, we will introduce such a model together with an explanation of set and local variables. First, however, we examine some variations on the theme established by new withdraw. The following procedure, make withdraw, creates withdrawal processors. The formal parameter balance in make withdraw specifies the initial amount of money in the account. Okay. Make withdraw balance. Okay. Make withdraw can be used as follows to create two objects, W1 and W2. Okay. So basically here we don't even define balance some way, but it's part of the construction, let's say, and then we can define W1. Yeah, we do not have to use let to make balance a local variable since formal parameters are already local. Okay. Observe that W1 and W2 are completely independent objects, each with its own local state variable balance. Withdrawals from one do not affect the other. We can also create objects that handle deposits as well as withdrawals, and thus we can represent simple bank accounts. Here is a procedure that returns a bank account object with a specified initial balance. See, these examples are much more easy to understand with respect to the examples from chapter 1 and chapter 2 that were ground on mathematics. Because to really understand the example, you should understand the general idea presented, the prefix notation, and in general the syntax of scheme, and then also the mathematics behind. Instead, here you don't have mathematics, you have very simple operations, and you can focus on the syntax and the concepts that are explained. So here we can define basically a bank account where you have an initial balance and you have the withdraw procedure and the deposit procedure. And then we have the dispatch procedure to understand what you want to do, basically, if you want to withdraw, if you want to deposit. Each call to make account sets up an environment with a local state variable balance. Within this environment, make account defines procedures, deposit and withdraw, that access balance, and an additional procedure dispatch that takes a message as input and returns one of the two local procedures. The dispatch procedure itself is returned as the value that represents the bank account object. This is precisely the message passing style of programming that we saw in section 2.4.3, although here we are using it in conjunction with the ability to modify local variables. So make account can be used as follows. We create an account and then we basically tell the procedure what we want. We want to withdraw and we have to explicit the number, or we can deposit. Each call to ACK returns the locally defined deposit or withdraw procedure, which is then applied to the specified amount. As was the case with make withdraw, another call to make account will produce a completely separate account object which maintains its own local balance. So these exercises seems to be nicer than the previous ones. So maybe I will restart to do exercises. Let's see. Section 3.1.2, the benefits of introducing assignment. As we shall see, introducing assignment into our programming language leads us into a thicket of difficult conceptual issues. Nevertheless, viewing systems as collections of objects with local state is a powerful technique for maintaining a modular design. As a simple example, consider the design of a procedure rand that, whenever it is called, returns an integer chosen at random. It is not at all clear what is meant by chosen at random. What we presumably want is for successive calls to run to produce a sequence of numbers that has statistical properties of uniform distribution. We will not discuss methods for generating suitable sequences here. Rather, let us assume that we have a procedure rand update that has the property that if we start with a given number x1 and form x2, x3, then the sequence of values x1, x2, x3 will have the desired statistical properties. We can implement rand as a procedure with a local state variable x that is initialized to some fixed value random in it. Each call to rand computes rand update of the current value of x, returns these as the random number, and also stores these as the new value of x. Of course, we could generate the same sequence of random numbers without using assignment by simply calling rand update directly. However, this would mean that any part of our program that used random numbers would have to explicitly remember the current value of x to be passed as an argument to rand update. To realize what an annoyance this would be, consider using random numbers to implement a technique called Monte Carlo simulation. The Monte Carlo method consists of choosing sample experiments at random from a large set and then making deductions on the basis of the probabilities estimated from tabulating the results of those experiments. For example, we can approximate pi using the fact that 6 divided by pi squared is the probability that two integers chosen at random will have no factors in common. Okay, that is that the greatest common divisor will be 1. To obtain the approximation to pi, we perform a large number of experiments. In each experiment, we choose two integers at random and perform a test to see if their GCD is 1. Then the fraction of times that the test is passed gives us our estimate of 6 divided by pi squared, and from these we obtain our approximation to pi. The hurt The heart of our program is the procedure Monte Carlo, which takes as arguments the number of times to try an experiment, together with the experiment represented as no argument procedure that will return either true or false each time it is run. Monte Carlo runs the experiment for the for the designated number of trials and returns a number telling the fraction of the trials in which the experiment was found to be true. Okay. Okay, I know this stuff. It's very similar to basically shoot points on a square and see how many of them fall inside a circle. That's another application of Monte Carlo to estimate pi. So now let us try the same computation using rand update directly rather than rand, the way we would be forced to proceed if we did not use assignment to model local state. Okay. While the program is still simple, it betrays some painful breaches of modularity. In our first version of the program, using rand, we can express the Monte Carlo method directly as a general Monte Carlo procedure that takes as an argument an arbitrary experiment procedure. In our second version of the program, with no local state for the random number generator, random GCD test must explicitly manipulate the random numbers x1 and x2 and recycle x2 through the iterative loop as the new input to rand update. This explicit handling of the random numbers intertwines the structure of accumulating test results with the fact that our particular experiment uses two random numbers, whereas other Monte Carlo experiments might use one random number or three. Even the top-level procedure estimate pi has to be concerned with supplying an initial random number. The fact that the random number generators inside are leaking out into other parts of the program makes it difficult for us to isolate the Monte Carlo idea so that it can be applied to other tasks. In the first version of the program, assignment encapsulates the state of the random number generator within the rand procedure, so that the details of random number generation remain independent of the rest of the program. Yeah, this is the central idea. The general phenomenon illustrated by the Monte Carlo example is this. From the point of view of one part of a complex process, the other parts appear to change with time. They have hidden time-varying local state. If we wish to write computer programs whose structure reflects this decomposition, we make computational objects, such as bank accounts or random number generators, whose behavior changes with time. We model state with local state variables, and we model the changes of state with assignments to those variables. It is tempting to conclude this discussion by saying that by introducing assignment and the technique of hiding state in local variables, we are able to structure systems in a more modular fashion than if all state had to be manipulated explicitly, by passing additional parameters. And unfortunately, as we shall see, the story is not so simple. Okay, so I think I'll stop here, and next time we will continue with the costs of introducing assignment. So see you in the next video. Ciao, ciao.